And so the buoyant force is actually more than the piece of wood. So when I let it go, the buoyant force is greater and it pushes it to the top. Whereas if I took something like this piece of brass and I put it underwater, let me clear that one off. And so if I make a little outline of my piece of brass here, I would say that the upward buoyant force on this piece of brass is equal to the weight. It's as if this thing was made out of water. It is equal to the weight of the water displaced. And so in this case, the actual weight of this piece of brass is more than the weight of the water that has the same volume as that brass, and therefore the weight of the brass is more than the buoyant force, and so it ends up sinking, and so the piece of brass sinks. And so the magical step right here is Archimedes' principle. And so I hope what you got out of this is, number one, why is there a buoyant force? And then number two, what is that buoyant force equal to? And so this is Archimedes' genius. The buoyant force is equal to the weight of the fluid displaced. Which then, of course, leads to whether something is going to sink or float. Because we know it will sink if the downward, that is the weight, is more than the upward, which is the buoyant force. Or the other way around, we know it will get pushed to the top if the buoyant force is more than the weight. And so deciding if something is going to sink or float in a fluid really depends on understanding where the buoyant force comes from. Well, watch this. Let me put some numbers in here, because I must say this is in words, and I have seen students over the years struggle taking these words and turning them into calculations at the end of the chapter here. And so let's do this. If I said, okay, how do you calculate the weight of something? And then how do you calculate then the buoyant force of something? Well, I'll start with the easy one, because we've done weight starting all the way back in chapter 3. Weight is just mg. But I'm going to add to that in this chapter. Mass could be density times volume. But here's where I want to be real careful. Let's take this piece of brass again. If I wanted to know the weight of this piece of brass, would I use the mass of the brass and therefore the density of the brass, or would I use the mass of the water? Well, clearly, if I want to know the weight of this object, I got to use the density of the object. Okay, so let me come over here and put a little 0 here for object. I'm saying O for object, not 0. And an O there for the volume of the object. This is why I want to point that out. This is where students get themselves confused. Because what is Archimedes' principle? He just figured out, and hopefully you followed his logic, that the buoyant force is equal to the weight of the fluid displaced. So I would say the buoyant force is also equal to a weight. And how do you calculate weight? mg. And if you're not careful, you're going to go, well, isn't that the same thing? No, it's not the same thing. Because this is the weight of the water displaced. This is the weight of the object, right? It would be, those are two different things. Me and my car don't weigh the same. We're two different things. Yes, it's the same word, weight. When you talk about how much do I weigh, how does my car weigh? But we are not the same object. We are not the same weight. So when I make this next step that say it is density times volume times g, I want to be a little careful here. Because the buoyant force is equal to the weight of the fluid that has been displaced. Therefore, I need the mass of the fluid displaced. Therefore, I need, and I'll put a little f down here, I need the density of the fluid. And then I need the volume of the fluid displaced. And so that's an important subtlety here. So, is there a buoyant force? Yes. What is it caused from? Well, the pressure difference. That is, the pressure is greater under it than on top of it. What is the buoyant force equal to? Well, it's equal to the weight of the fluid displaced. How do you calculate it? You calculate it like you would calculate any other weight. It's density times volume times g. And to decide if something is going to sink or float, you would want to then compare this to this. And so I would say, for something to sink, the weight of the object would need to be greater than this buoyant force. And if we put in this logic we would have the density of the object times the volume of the object times g. It needs to be greater than the density of the fluid, the volume of the fluid times g. And so that's what I get when I put my logic and my math to these words. So I'll say it again. What is the buoyant force? Here it is. Would you like to know the answer to, I'll call it half the homework problems here in this chapter? It's related on Archimedes' principle. This chapter has two important principles. One is Archimedes and one is Bernoulli's. And in this Archimedes principle, it says that the buoyant force is equal to the weight of the fluid displaced. And this is how you calculate it. And to then decide if it's going to sink or float, I would have to calculate its weight. And so something to sink, its weight would be more than its buoyant force. Now, of course, for something to float, well, let me hold off on floating. Maybe you could just see it would be just the opposite of sinking. But I can simplify this a little bit, and the g's would cancel off. And here's something that would only be true if it's completely submerged. But remember, if something is sinking, it eventually will get submerged. Maybe when it first starts sinking, it's not completely submerged. But if I start with this piece of brass again, I lost the piece of brass, and it sinks. All right, well, let me just get the rock. But I'll just grab another piece of brass. I'll grab this piece of brass. But when I first put, and I'll clear this off a little bit, this piece of brass underwater, maybe right now, the volume that it is displacing of the fluid is not the same as the volume of the object. Because there's the object, but there's the water level. So as long as some of it is above the water line, I would say the volume of the object and the volume of the displaced fluid aren't the same thing. But ultimately, if it is going to sink, okay, and it goes completely underwater, and I make an outline, I would say, once it's completely underwater, the volume of the object and the volume of the fluid are the same. So if I take that over here to this discussion, then I will cross those out. And maybe I should say volume of object equals volume of displaced fluid if completely under, and I was going to say water, but maybe I should say fluid, just to keep reminding you that it's the same physics if I was in, some other fluid like petroleum or isopropyl alcohol or even the air. And if I cancel those off, I end up with, if the density of the object is greater than the density of the fluid, it will sink. In fact, sadly, sometimes I hear that in just common speak. Sometimes I'll be at a social gathering and somebody will say, oh yeah, things sink if their density is more than the fluid. And that's true, But that's the conclusion. That's not the reason. The reason they sink is because the weight of it is more than the buoyant force. And the buoyant force is equal to the weight of the displaced fluid. And if you take that logic all the way through, you finally come up with a simple answer that any object that has a density greater than the fluid it is in, it will sink. So, let's take the piece of brass. Here's that piece of brass, but I've got this second one over here now. These pieces of brass have a density a little bit greater than 8 grams per cubic centimeter, where water has a density of 1 gram per cubic centimeter. That's probably worth remembering, water. We use it so much. So water has a density of 1 gram per cubic centimeter. So basically, anything that has a density greater than 1 is going to sink when it's in water. And anything less than a density of 1 is going to float, again, when it is in water. So brass definitely sinks. Like I said, has a density of about 8. This rock, which has a density of about 5, sinks. The wood, which has a density of about 0.6, floats. The styrofoam floats. At least in water. Because let's take this piece of wood and put it in something of a different density. Remember I said the air is a fluid? So let me put the piece of wood in the air. Oh! Did it sink or float? Clearly it sunk. In fact, the density of the air is so small. Well, what is it? 1 kilogram per cubic meter. So that'd be 0.001 gram per cubic centimeter. So only things that have a density less than the density of air will float. And this piece of wood has a density far greater than air. So it sinks. I have a density just under 1. When I go swimming, I dive into the pool, I float. Now, not by much, but I float. In fact, if I were to hold my breath and go like this, the water level's right about here. Which is too bad, because if I want to take a breath, I got to come and go like that. It'd be nice if I floated a little bit higher. But I float right here. But I float. And that tells me my density is less than 1. But when I'm in the air, I don't float. I don't go up to there. In fact, the only thing I can think of that really floats are these helium balloons, these hydrogen balloons, or hot air balloons. They float. They have a density less than the density of air, so they float in air. Everything else sinks. And I think it's because of that we forget that the air is also a fluid. But just like things in the water can sink or float, things in the air can sink or float. If you ever have the chance to go into a very, very salty lake, not the ocean, although you'll notice it with the ocean, because when I go into a swimming pool and tread water, I can tread okay, I can almost back float. But when I go into the ocean, I can back float really easy, because the density of the salt water is higher. And my body has the same volume. So remember, the buoyant force is equal to the weight of the displaced fluid. So when I get into salt water, I displace the same volume when I take a breath and go underwater. But because the density is greater, there's a greater buoyant force on me. And I float much easier in salt water. And the reason I say, if you ever get a chance, a good one in California is Mono Lake in the Eastern Sierras. It is really fun. You just kind of wade out into the water. And it seems kind of gross because it is extremely salty. And there's a lot of flies in the area, because that's really the only thing that can live there is these little shrimp that then the flies eat on, and then the seagulls. And so that's, I think, about the only 3 species that live in that lake. It is so salty, though, that when you walk out into it, about the time you get about neck deep, you float. And so instead of having fresh water where I have to displace this much volume to equal my weight, because the density of the salt water is more, I only have to displace this much. And of course, what's really nice about that is now I can go out into this lake. I'm not even touching the bottom, and my head's right here. And I can breathe. I can relax. I don't have to tread water. I just float. And the seagulls look weird because, you know, I'm used to seeing the seagulls in our ocean. You see them there and they're floating really high. It's like they can't even get their legs into the water. They're just like bobbing on top of the water, and they can really barely get in the water. They're just so incredibly buoyant. Oh, which brings me really to this. Here's a fun one to do. I've got some beads that are in my fluid. Do they sink or do they float? And aren't they kind of in the middle? How does that work? Well, I tricked you a little bit. These are not the same fluids. This fluid down here is salt water. This fluid up here is isopropyl alcohol. Actually, it might be methanol alcohol. I think it's isopropyl alcohol. Don't remember, but let's call it alcohol. So we've got alcohol and we got salt water. But salt water has a density greater than 1. Alcohol has a density less than 1. So these beads sink in the alcohol, float in the salt water. They have a density that's between the two. Here's the best part of this. I'll shake it. You see, when I shake it and I mix it up, I get a density that is somewhere between the alcohol and the salt water. And if I leave it alone, the white beads have a density that is less than the mixture. The blue beads have a density that is more than the mixture. So the blue ones sink and the white ones float. And it gets better. Watch it now. The alcohol works its way up through the beads and goes above the beads. The white beads. The salt water goes down below the blue beads. And the whole thing comes back together the way you saw it when I got started. And it's all based here on Archimedes' principle. Well, it looks like, again, I've talked way too much, but this is just kind of a fun one to do. But I should show you a quick other thing so we have a good stopping point, and then we'll go to our 20-minute break, and then we'll finish up the chapter. But watch this for a moment. If I take wood, and what I do with that piece of wood now, you've watched it float many times. And I think because it's wood, sometimes people go, oh, well, it floats because it's wood. And I want to emphasize, no, it doesn't float because it's wood. It floats because its density then is small enough that by the time you figure out how much does it weighs less than the buoyant force. And so, clear that off. But if I put this piece of wood underwater, then I would say, yeah, gets pushed to the top. But ultimately, it has to do with buoyant force and weight, which comes down to density of the two, the two, which is one is the object and one is the fluid. I say that because I have another piece of wood. This is a piece of mahogany, and so this is a hard, dense wood. And so if I put this in the aquarium, it sinks. And seeing wood sink is just, I think, a little surprising because most woods are less dense than water and most woods do float, but not all of them do. Likewise for rocks. You've already seen this big rock here, which has a density of about 5, which is then greater than the water, which is 1, and so I put it in here and the rocks sink. And it doesn't sink because it is a rock. It sinks because its weight is more than the buoyant force, and its weight goes back to its density, and so its density is more than the density of the fluid. But other rocks, and so this nice volcanic rock right here, is a rock, but its density is less than 1. And so it floats. And so seeing a rock float or a piece of wood sink isn't normal, but it can happen. It has nothing to do with the material. It has to do with these forces which go back to its density. Well, one more piece here and then we better wrap it up. But maybe and even the harder one is, let's look at something that is floating. Let's take a boat. And let's come back to our mathematics over here. If I come back here and say, okay, now it's not sinking, so I wouldn't say its weight is greater than its buoyant force. In fact, I would come over here and say, because it is floating, and so let me go here and say, okay, let's look at something that is floating. Then I would say the weight of it is exactly equal to the buoyant force. See, gravity is pulling down on the boat, but the water is pushing up on the boat. Those two are equal. And if we do the same mathematics here, and we said, okay, well, what is the weight of the object? I would say it's the density of the object times the volume of the object. Volume of the object times g. That has to then equal to the density of the fluid times the volume displaced of the fluid times g. And so we have almost the same equation, except over here we had an inequality. Now we have an equality. I can still cancel off the g's, but I cannot do the next step. Remember, this step said that the volume of the object and the volume of the fluid were the same, at least once it gets submerged. But if it's floating, it's not submerged. And you can see that with the boat. You can probably see it better with the piece of wood. You put this piece of wood in here, and you can see that the part that is underwater, the volume underwater, the volume being displacing the fluid is not the same as the volume of the piece of wood. And so I cannot say that these two volumes are the same, and therefore I can't cancel them off. But I can do this. I can say that if I rewrite this as a fraction, the volume of the fluid being displaced over the volume of the object would be the same as the density of the object over the density of the fluid. And if I stop and think about what this means mathematically, this really is the volume underwater of the whole object. So you might say this is the stuff underwater. How much of it is underwater? And so that piece of wood looks like about maybe 60% is underwater. So the volume placed of the fluid and the volume of the object, this is probably roughly for my piece of wood about 0.6. And that makes total sense because the density of my piece of wood is 0.6 and the density of the fluid, water, is about 1. And so the ratio of the densities is the same as the percentage that is underwater. And so something that has a density very, very close to 1, and it looks like about the only thing I have that's close to 1, and it's not that close, but still less than 1, is this piece of wood. And so it's mostly underwater. But since we talked a lot, maybe I'll just do one more here. The density of this styrofoam is really low. It's like 1/10. And so only 1/10 of it maybe a little more than that looking at it, is underwater. And so how much it floats above the water is an indication of that. And so you can see that really well with the boat. The boat, this little plastic boat, I would say floats pretty high because it is really mostly just plastic. But what would happen then if I put a little bit of weight in my boat? And so as I load my boat with gear and people, you will hopefully see that it's got to go deeper into the water because, again, it weighs more. And to support it, it has to have a bigger buoyant force. To get a bigger buoyant force, it has to displace more water. So again, the weight of all the gear in the boat is equal to the buoyant force. It's just, it weighs more with all this gear, so we have to have a larger buoyant force. And because of that, it has to sink a little bit deeper. Well, I better cut it here because I've still got some fun things to show you with Bernoulli's principle, but these fluids can be really challenging, and so the homework can be a little challenging. We'll see how that works for you, and we'll take any questions that you have, but I'll call it quits for now, and let's take our 20-minute break, and I'll see you in 20.